All right, so now we're going to introduce the idea of boundary value problems. So previously we had primarily focused on what are called initial value problems, right? So let's consider that. So let's consider an initial value problem. And in particular, let's consider sort of a second order system. Well, not systems, just a second order differential equation. Okay, so we have y double prime is equal to f of t, y, and y prime. And then t is in some interval from a to b. And with initial conditions, y at a is equal to alpha, and y prime at a is equal to beta, for example. Right? So we can write this as a system. First order equations. Right, which we discussed before. So let's say x1 prime is equal to x2, and then x2 prime is equal to f of t x1 and x2, and then x1 at a is equal to alpha, and x2 at a is equal to beta. And of course we talked about, one-step methods. It's like for solving these things. So again, these are sort of initial value problems because, as the name implies, it's like the data you're given is at the initial time. So let's consider an alternative sort of set of boundary conditions, which are called two-point boundary value problems. So let's consider instead a two-point boundary value problem. Okay, so let's say y double prime is equal to f of t, y prime, and we have y at a, which is alpha, and y at b is beta. Okay, so now we have a different set of initial conditions. Well, they're no longer initial conditions, but they're boundary conditions. So you specify y at the two endpoints. T is from a to b, right? And you can ask, well, can you solve this instead using boundary conditions instead of initial conditions? So let's look at an example of this. Okay. Okay, so let's say we have y double prime plus y is equal to 0. Okay, so we can write down the general solution of that second order constant coefficient linear differential equation, right? You probably know the answer to this already. Y of t is equal to some linear combination of sines and cosines, right? So it's c1 sine of t plus c2 cosine of t, right? So this is the general solution, right, with coefficients C1 and C2, right? So, so we can look at some boundary conditions. Okay, so we could have y at 0 is equal to 1, and y at pi is equal to 1. All right, so so the point basically then, as was the case with what you would have done if you had an initial value problem where you try to solve for the C1 and C2 to satisfy the initial conditions. Now I'm going to solve for C1 and C2. It's like so to satisfy the boundary conditions. Okay, so so all that entails obviously is substituting t equals to 0. It's like to this right hand side, and then writing down an equation which C1 and C2 satisfies. So this is equal to C1 times 0 plus C2 times 1. And then, okay, so this is, and then at pi, it's like this is C1 times 0 minus C2 times 1. Okay, so that's a problem, right? Because this implies that C2 is equal to 1. It also implies that C2 is equal to minus 1, right? So that's a contradiction, right? So the point is that the equation does not have a solution. A solution which satisfies these boundary conditions. Okay, so that's problematic. Okay, so if you recall, you know, it's like the way you can study this, right? The solvability, it's like of initial conditions and boundary conditions, was to essentially evaluate it's like the basis, it's like for the general solution at the data, right? So if you look at this, so if I call this term y1 and this term y2, right, then I can look at this matrix consisting of y1 at A and y1 at B, and then y2 at A and y2 at B, right? And then A is 0 here, and then B is equal to pi, right? All right, so y1 is sine at 0 is 0, right? And then maybe let's write this the other way. Okay, y2 at A, and then y1 at B, y2 at B, right? So these are the coefficients, 0, 1, 0, minus 1, right? So you can check that that obviously has determinant 0, so that system is not invertible, right? So again, the bottom line is that in general, it's like you may not be able to solve that system of equations. Okay, so that's basically what's happening here, right? You sometimes can solve it if the data at 0 and 1 is somehow in the image of this operator, but in general, it's like this is not solvable. Okay, and if you recall, you did something similar. It's like with initial value problems where you, instead of evaluating it at different times, like you sort of took the y1 and y2 and then the derivatives, right, for the next row and so on, right? And then that matrix itself has to be invertible. It's like in order for you to be able to solve the system of equations. Okay, so something similar happened here with initial value problems and the solvability for the initial conditions. Okay, anyway, so the determinant, right, is equal to 0, right? So it's not invertible. Yeah, and if you recall, it's like the reason why you did this was because you said that y is equal to the system you're trying to end up solving for is y at A, right, and y at B, which is the data you're given, right, is equal to this matrix y1a, y2a, and then multiplied into c1, c2, which is the unknown, right, and then y1b, y2b, right? So this would be just c1 y1a plus c2 y2a, and then c1 y1b plus c2 y2b. right? Yeah. So anyway, solving for C1 and C2 in terms of the boundary data, right, involves inverting a linear system like this, and in particular having the invertibility, it's like of this matrix comes into play. Okay, so that's sort of the reason why, in general, it's like with this kind of boundary data at time 0 and time pi, you may not necessarily be able to solve. It's like for arbitrary choices of boundary data here. Okay, anyway, um, so so if you recall, it's like your theory of systems equations, right? You could end up when you have a linear system, it's like which has a matrix, right, which is not full rank. You could have this situation where there are no solutions. You could also have a situation where there are infinite set of solutions. So let's sort of look at this case. Let's look at case 2, right? So so if you had y of 0 is equal to 1 and y of pi is equal to -1, right, then your condition is that 1 is equal to c1 times 0 plus c2 times 1, and -1 is equal to c1 times 0 plus c2 times -1, right? So so this tells you that c2 is equal to 1, right? And c1 can be anything, right? Okay, so you have, again, an infinite family of solutions, right? So we have the infinite family of solutions. Well, let me maybe put it this way. There's a one parameter family of solutions where it's parameterized by this C1, for example. Okay, all right. So let's look at one other possibility. It's like where you have unique solutions. And as I sort of alluded to, it's like in this kind of discussion here, you can't have a unique solution unless A and B were different from 0 and pi, right? They have to be something else. So let's see what you could do. All right. Okay, so let's look at this third case. Okay, so let's say I have y at 0 is equal to 3, and then y at pi over 2 is equal to 7. All right, and then this gives you equations 3 is equal to c1 times 0 plus c2 times 1, and then 7 is equal to c1 times 1 plus c2 times 0. And this, again, just comes to the fact that y1 at A, y2 at A, y1 at B, and y2 at B now looks like 0, 1, 1, 0, right? So that matrix is invertible, okay? And so this obviously tells you that C2 is equal to 3 and C1 is equal to 7, right? So you have y of t is equal to 7 sine of t plus 3 cosine of t, and then you have a unique solution. Okay, so this is invertible. Okay. All right, so anyhow, so that just gives you, it's like some possibilities. It's like of what might happen. It's like if you have a boundary value problem. Okay, so so let me just remark that the question of existence uniqueness of solutions is hard, right? It's difficult. Right, because if you think about it, right, the analysis which we did here right, relies on you actually knowing what the general solution looks like, right? So that's not always easy to do, depending on what the differential equation is, all right? So, you know, knowing whether or not it's like you have this combination of boundary conditions, it's like which is uniquely solvable, that's hard in general, okay? All right, so let me say one theorem it's like towards that end, about when you can say you do have existence and uniqueness. Okay, so the theorem is as follows. Right, if the functions f sub y, which is and f sub y prime, so these are partial derivatives of f respect to y and y prime respectively, are continuous, on the domain D, which is this product of an interval in time and then sort of open intervals in space, right? Okay, and if the following conditions are true, the first one is that fy ty y prime is greater than 0 for all ty y prime in this domain, and the supremum over ty and y prime over this domain D of the absolute value of fy right is finite. Okay, then the boundary value problem y double prime is ty y prime, right, where t is an interval from a to b, and you have boundary data y of a is equal to alpha, y of b is equal to beta, and that's a unique solution. Okay, so anyway, so that's at least one of these existence and uniqueness theorems. It's like for boundary value problems. Okay, so let me just stop here for now.